to get longer. So the Earth will be rotating on its own axis more slowly, and the moon will go further and further away. And eventually, that rotation of the Earth, that day length, will be exactly the same as the moon's orbit. And you'll only be able to see the moon from one side of the Earth.
Welcome to the Podcast for Inquiry, brought to you by the Centre for Inquiry Canada, a national educational charity supporting your community for reason, compassion, and secular humanist values. You have answers, we have questions. I'm your host, Leslie Rosenblood, board member and secular chair for CFIC. Welcome. My guest today on Podcast for Inquiry is John Moores. John is a planetary scientist and associate professor at York University. He is a member of the Royal Society of Canada, formerly served as the science advisor to the President of the Canadian Space Agency, and has contributed to 5 NASA and ESA-led space missions. He is the co-author of Daydreaming in the Solar System, which imagines a future when visiting other planets is as common as hiking in a national park. The book is also grounded in the latest scientific knowledge about planetary geophysics. In addition to talking about the book, John also answers some of my pressing questions about the solar system, including how do planets and moons become tidally locked? Why are most planets in the solar system aligned in a plane? Why are there gaps in Saturn's rings? Is there life elsewhere in the solar system or in the universe? To answers to all of these and more questions, it's my pleasure to bring you my conversation with John Moores on today's Podcast for Inquiry. John Moores, thank you for speaking with me today on Podcast for Inquiry.
My pleasure to be here.
We're here today to talk about your book, the one that you co-authored with Jesse Rogerson, called Daydreaming in the Solar System. Now, I'm a little bit of a space geek because I'm a geek and space, right? That's it's always of interest to me, but I am not an astronomer and I've never formally studied. So even though this book is actually geared towards people like me or people that know a little bit less than me, to basically beginners, and it was great. I want to start with the structure of your book because it's different than pretty much any other book that I've read, and I found it very engaging. So I think you know what I'm talking about. Can you tell us what makes your book unique in the structure of each chapter?
Well, absolutely. So each chapter we set up as a combination of fiction and of science writing of fact. So what we do is we start each chapter with a story, which imagines what it would be like to be doing an activity on another planet, almost as if you were visiting a national park. And then what we do is we have the second section of each chapter that talks about the science that makes that possible and how we know that that environment would actually be like that.
Yeah, so and there was a little bit of science fiction involved. Right? You had people in an early chapter on the surface of Mercury, and that's not something that we have done, or I think at this point can do. But it seemed like the extrapolation was not huge on in that. And so, how did you decide? Like, did you just decide to make up the technologies that you needed to traverse each aspect of our solar system, or did you try to minimize it? How did you come up with making it as close to our current capabilities as possible, even when we're not currently capable of doing the things that you describe in the first half of each chapter?
Well, it's a very good point. And one thing that we did was to try to background the technology a little bit. A lot of science fiction is really about, these futuristic technologies and thinking about where engineering could go. We wanted to focus a little bit more on the science, on the landscape, on what kind of world this is, which is something that we know a lot better. But of course, there were times when your astronaut has to be alive and your astronaut has to be able to do the activity. So we have to imagine things that could happen that are in the potential realm of possibility, even if today they would be very big undertakings to do. The imagination here is thinking that maybe in the future, this might be something that is accessible to, people who are not billionaires, for instance, to go and try out some of these things.
I learned a lot from your book, which is great. I'm always enjoying. I always enjoy reading, and science fiction is my favorite fictional genre because just the exploration of ideas. So the combination of, extending the imagination of what could be, and compared to what is, combined with here's what we actually know. Um, I know that when it comes to the moon, we always see the same part of the moon, and we call it the dark side of the moon because it's on the far side, and we never see it from planet Earth. And the reason for that is I've heard the term, it is tidally locked. Now, to me, the tides are the oceans, right? And they rise and fall because the moon comes closer or further away. And so it actually pulls the water up and down. But and so that to me is what tides are and what tides mean. And I've heard the phrase tidally locked, but I don't understand the mechanics. And you explained it a little bit in your book. So can you say what tidally locked actually means and why the moon can't spin as it orbits the Earth?
So your timing is impeccable, because this was one of the lectures that I gave this week in my planetary geophysics course here at York University.
I'd like to say
So,
that I stuck in and lobbed you a softball question, but no, this is just a happy coincidence.
oh yeah, so the thing that's important about tides, and the reason we use the word tides when you get these configurations between two bodies, often it's a planet and a satellite, but you can also get it between a star and a planet as well. Uh, what's going on is there's a way here that involves the tides that allows these bodies to essentially trade momentum and energy back and forth with one another. And any system of a planet and a satellite, anything that's orbiting, you're going to have that lowest energy state, the state that the system wants to be in, that it's trying to get towards, is going to be a state where you've got the planet and the big satellite looking at each other, so they each have the same face pointed towards each other. So the rotation rate, the day of the planet, is the same as the rotation of the moon. We're not there yet entirely. Usually the satellite, because it's smaller, it gets locked in place first. So it has its day the same length as its orbital length. The Earth isn't quite there yet. And the reason that this happens is when you get an ocean tide, that also happens on the land as well. You have this sort of relaxation, this rising towards the satellite. But everything's in motion, and it takes time for rock and for water to move. And so by the time the rock and the water has actually responded to the moon's gravity, the Earth is rotated around just a little bit. So now that bulge is actually pulling on the moon. It's sort of yanking it forward just a little bit. So the moon speeds up, the Earth's rotation slows down, and the Earth does the same thing with the moon. It raises a tide on the moon, same as the moon raises a tide on the Earth. And because the Earth is the big bully in this scenario, the moon gets locked first, but eventually, billions of years from now, the moon will have its revenge.
And so will the Earth still be spinning relative to the sun? It just won't be spinning relative to the moon, or will the Earth basically become largely will stop its spin because of the moon's presence?
The spin will continue. It'll just be slower than it is today. So the orbit of the moon and the rotation rate of the Earth will be the same eventually. So it's not going to completely stop, but it will be slower than it is today. In fact, the moon started closer to the Earth than it is now when it first formed, and the day was much shorter on the Earth. I believe, if memory serves, it's something like 17 hours is the estimate for when the moon was first formed. And so, with time, the system's been evolving into the state where
Well,
it is right now.
that's a huge difference between 17 and 24 hours. What times, like when did the Earth have a 17-hour day? Like how long?
So that would have been, oh yeah.
Yeah, or just like over what time scale did the Earth's day increase by 7 hours? Like that's a big increase.
Yeah, that's over about 4.5 billion years. So the moon formed very early on in the Earth's history, not long after the Earth itself formed. So for most of the time that the Earth's been around, it's had a satellite, and the two of them have been evolving together.
So does that mean that in another 4.5 billion years, when the Earth and the Moon or when the Earth are even closer, when the Earth is more tidally locked to the Moon, the day length will continue to increase?
That's right. It'll continue to get longer. So the Earth will be rotating on its own axis more slowly, and the moon will go further and further away. And eventually, that rotation of the Earth, that day length, will be exactly the same as the moon's orbit. And you'll only be able to see the moon from one side of the Earth. So there are places in the solar system where this has already gone to completion. So if you look at Pluto and Charon, Pluto being the dwarf planet, formerly the ninth planet of the solar system, but now a dwarf planet, it has a very large satellite that's very close called Charon. And Charon is tidally locked to Pluto, and Pluto is tidally locked to Charon. So you can only see that satellite from one side of Pluto.
Interesting. One thing that I learned from your book that I had no idea about is that Mercury is almost tidally locked to the sun. I didn't realize that I didn't know that could happen with planets. I thought that was only a phenomenon with moons. And I was going to ask why that is, but I think you've already answered that. So I want to ask about another aspect of Mercury, and that is there are two definitions of a day, and they on Earth they're in terms of duration they're almost the same, but on other planets they can be very different. So can you tell me, when we say a day, it can mean one of two things. What are they? And talk about how different they are specifically on Mercury.
That's right. For the Earth, they're very similar. So it's very small difference in between them, and for a lot of planets, it's like that. But Mercury is the outlier here. So the two kinds of day you can have, one is a sidereal day. So that is the rotation of the planet compared to the fixed stars.
So sidereal. I just want to make is that that's how it's pronounced? Okay, right. I came across the term for the first time reading your book, so I thought it was sidereal. So thank you. Sidereal is an improvement in my pronunciation for the vocabulary. Okay, so what is a sidereal day?
So the sidereal day, that is just the rotation of the planet with regards to some place that's fixed in space. So we normally compare it to the stars because the stars don't move very fast at all. So comparing to the fixed stars, you've got this rotation rate that's the sidereal day. But the thing is that between the start of the day and the end of the day, the Earth moves around in its orbit just a little bit. So the angle to the sun changes. And the length of day that's more useful to folks who are living on the Earth, or if you're sending a spacecraft to somebody who has a spacecraft on a planet, is essentially the cycle of the sun rising and the sun setting. So we call that the solar day. And the solar day is going to be just a little bit longer because you've got that movement along the orbit. At the end of your sidereal day, the sun is in a slightly different position. And so that means that your solar day lasts just a smidge longer on the Earth. If you go to a place like Mercury, it's a huge difference because the rotation rate of Mercury is so slow. The solar day actually lasts 2 years, 2 entire revolutions around the sun, 2 Mercurian years, I should say.
That 1 day equals 2 years blew my mind when I read that. Just
Oh yeah, it's the way that it's tracking, right? So that it actually rotates in such a way because of the almost tidal locking that you kind of get that really weird setup that you're in that sort of 3-2 resonance, we call it. So every time Mercury goes around the sun twice, it turns on its axis 3 times, and it turns out that that is just the right amount to keep, you know, the day nice and long. So it's not quite always pointed at the sun the way the moon is always pointed with the same face at the earth, but the rotation rate is such that, you know, every time you go all the way around the sun twice, you get those that one single solar day. And so we were thinking this is a great place to go for a walk all the way around the planet in one
And
day.
you can always stay in sunlight or in darkness.
Exactly. Darkness is safer, but you want a little bit of sunlight. You want to kind of see the terrain that you're walking through a little bit, but not too much. You don't want to get into that self cleaning oven
Right.
territory.
Now, you mentioned something that I just want to come back to. You said that in terms of the Earth, because we've moved just a little bit as around the sun as the Earth rotates, the day is just a little bit longer. And I think you used the word always. Uh, is it possible that if, like, the Earth was spinning the other way, or the rotation of the planet was the other way, um, that the uh, that the solar day could be just a little bit shorter, or is it always going to be a little bit longer than the sidereal day?
I have to think about that in my head. I think you might be right that you might be able to get a shorter solar day than a sidereal day, depending on the relative rotations. For most planets, they actually rotate on their own axis and they go around in their orbit in the same direction, but it's not universally true.
Okay, so that actually leads me to, there's a lot of uh, similarities in the solar system that have always kind of puzzled me. So, uh, and the one that I have noted but have never understood is why, for 7 out of the 8 planets, or 8 out of the 9 if you want to include Pluto, the dwarf planet, uh, with the exception of Neptune, all of the planets are essentially in a plane. Like, if you look at where they are, they're all more or less uh, they're all very, very close to orbiting in the same way. Like, they're all like this, and they're just further out or closer in, and they might not be perfect circles or perfect ellipses, but they're all on the same level. And I naively, I would think that planet formation would be more or less random, so that they would be like, one would be essentially, from a particular perspective, one would be vertical, one would be horizontally orbiting the sun, there'd be diagonals, and they would all be on like essentially random angles. But when all but one are orbiting the same way, that's I don't think that strikes me as highly unlikely that that's simply a coincidence. So, can you explain why the the planets are mostly all aligned in that sense? And if there's a reason why they're all aligned in that way, why is there an exception?
Well, the one that's the furthest from being, you know, right in that plane is going to be Pluto out of that bunch, and that's because Pluto is kind of a weird place for many reasons. But you know, all of the classical planets and Uranus and Neptune are pretty darn close to being in that plane. It comes from the early solar system and the way that the solar system formed. So at the very beginning, you had a sort of a shock wave that went through a nebula, which had a lot of gas and dust in it. And that shock wave, you know, piled up material ahead of it. To use an example, because it's winter here in Toronto, you know, like a snowplow or a, you know, or a bit of a shovel. And when you got enough material clumping together, that could collapse down and to start to spin, and the center of that became the sun. And the way that this works with angular momentum, you end up with anything that is not in that plane essentially getting thrown out of the system. So you have all of your material in the early solar system sitting in this plane. It's all rotating in the same direction. That's why all the planets rotate in the same direction. And when the planets have their own rotations, they're on their own axes, that's why that is usually in that direction as well. So over time, as this disk of gas cooled, you had material that would condense out of it, and that material clumped together to form the planets over time. As you go further out, the influence of this effect gets smaller and smaller, and the influence of the sun's gravity gets smaller. So you get bigger and bigger, what we call inclinations to this flat plane of the solar system. And eventually, when you get out more than a couple hundred times the distance between the sun and the Earth, you get into the place where we have sort of this cometary cloud called the Oort cloud. And the Oort cloud really is completely random. It is a spherical shell of material around the sun that goes halfway to the next star.
Okay, interesting. Thank you. I've wondered that for a long time. You mentioned that planets all spin the same way due to this effect. Do all of the planets orbit in the same direction as well, or does like one planet go this way and like what clockwise from a particular perspective, and another planet goes counterclockwise?
No, they're all in the same direction. It turns out if you have a planet that's going in the other direction, that doesn't tend to be stable, and those are the bodies that get kicked out of the solar system by the dynamical effects. So the direction for our solar system is if you look down on the North Pole, so looking down from on top of the solar system, everything rotates counterclockwise, and we call that direction prograde. And by the way, if you're going the other direction, we call that retrograde.
Okay. So it just, and whether it's prograde or retrograde, that just is essentially a random event when the solar system is first forming. But then anything that tries to go in the other direction, it gets close to a planet at some point, and then it's far away, and then those interactions kick the one, the non-conformer out. Is that basically how it works?
Exactly. Those things can get removed from the solar system, or they get incorporated into other planets. So when we were talking about the tidal exchange a few minutes ago, because the Earth is rotating prograde and the Moon is orbiting prograde, you have this exchange of energy that will eventually result in the system being stable, with one side of the Earth looking at the Moon and one side of the Moon looking at the Earth, and just going around in lockstep. If the Moon was traveling in the other direction, or the Earth was rotating in the other direction, then the Moon would spiral in until it impacted with the Earth, and then that eliminates the body that was going retrograde.
All right, so that I want to ask you about another anomaly in the solar system, and it's a fairly obvious one, and that is Saturn's rings. So they're made up, as you say in the book, of millions, billions, trillions of rocks, from tiny little particles like a grain of sand to houses or tens or hundreds of meters wide in one dimension or another. But everywhere else in the solar system, we had those either coalesce into moons or planets of their own, or they got sucked into whatever planet that had formed nearby. So why didn't they coalesce into moons of their own or fall into Saturn's gravitational well? Why does Saturn have rings? And I'd also like to ask, when you're answering this question, think of another one, which is, why don't any other planets have rings? Like, why is it only Saturn that these conditions apply that gave it rings?
So let me actually start with that one, because sure, though Saturn may have the brightest and the showiest set of rings, all of the giant planets have rings. It's just that they tend to be a little bit more muted. Sometimes you can only see them from spacecraft, with the sun behind the planet and the light coming through.
Jupiter and Neptune, Uranus, they all have rings as well.
Indeed.
Okay. See, I'm learning not just from your book, but from talking to you. This is wonderful. Thank you.
Oh, you're welcome. It's such a fascinating system, Saturn's rings. It's another one of these examples of that whole dance that you have with orbital mechanics and angular momentum, creating this structure that is incredibly flat. Like the flatness of Saturn's rings is just
Yeah.
astounding. But from one end to the other end, it's 160,000 kilometers across the rings, but the ring thickness is only like 30 meters or about
Okay,
100
so
feet.
so
So
like my question about the planets being on a plane, why is that? Like that does not intuitively that does not make sense. There ought to be a sphere around the planet for whatever, like, but it's not. So what makes it, instead of a cloud surrounding a planet, coalescing into this incredibly narrow band of rings instead of encircling or in sphere, uh, not encircling, but encapsulating the entire planet.
right. So there's a couple of things here. So one is just the way that the system is set up is it wants to stay in the ring plane, and if particles deviate from the ring plane, then there are forces that try to pull them back down. And so, you might bob up and down relative to the ring plane over time, and as that damps out, then you settle down to being right in the ring plane. Or if you run into something, then you end up with a bunch of things that are then very close to the
Go
ring
into a
plane.
little bit more detail on that. Like, what are the forces bring that bring things into the ring if it's starting to deviate?
Well, again, this is where you'd have tidal forces, and the rings itself, like the ring particles themselves, have gravity. So if you were to take a ring particle and you were to disturb it upwards, it would feel a tidal force, a gravitational force, trying to pull it back down to the ring plane from all of the other particles. They're very much like, hey, that one that got out of line, get back here, and have some more orderly motion with us. And partly this could have to do with the origin of the rings. This is something that's still an active area of research, and there are different camps. Some people think that the rings are old, some people think that the rings are new. And one of the leading theories for where the rings came from is that maybe you had one of these satellites that was being pulled in towards Saturn. Its orbit was decaying, and once you get to a point called the Roche limit, that's a fancy name for a spot where you would experience more tidal forces from the planet, from Saturn, than gravitational forces with yourself. So Saturn basically pulls that body apart. And the main evidence for this is the fact that the rings of Saturn are incredibly pure in water ice. That's actually really weird. And one of the ways that you could get that is if you had a satellite, and all the satellites in the all the big satellites in the solar system, all the planets have gone through this process that we call differentiation that lets them sort of settle out into different layers with different densities. So for the Earth, we have the core, which is made of iron, and then we have the mantle, which is made of dense rock, and then lighter rocks are in the crust. So with Saturn, if you had an object like this that had an icy layer, and once it passes that Roche limit and material starts coming off of the outside to form the rings, you could pull off this really pure water layer, and then all of the rock and all of the iron, maybe that just got swallowed up by Saturn. By that point, the satellite had gotten all the way to the atmosphere, and so you can just hide all of that in the planet itself, and you're left with this really watery layer of rings that used to be just one part of this former satellite.
Oh, wow. Interesting. Now, you mentioned when we talked about the planets that have rings, we listed the solar system's gas giants. None of the rocky planets have have rings, or at least you didn't mention them when we talked about that. So, are rings a property of gas giants? Do they only form around gas giants? Is it just a coincidence that it's the gas giants that have rings in our solar system? Can you talk about the relationship between those two?
It does seem like the gas giants are correlated with having rings in a way that the rocky planets just aren't. And I think there's probably a couple of bits and pieces that go into it. I will admit this is not really my area of research per se, but you've got a lot more material and a lot more gravity going on out with these giant planets. They're in a part of the solar system where the disk from which of gas and dust from which the planets formed was able to cool more quickly because it's further from the sun, and so more things were able to condense out, and so they have access, in a sense, to some more materials there. And there's a lot of complicated dynamics going on in the outer solar system. You've got, you know, dozens and dozens of moons around every one of those gas giants. Within the inner solar system, you've got Mercury and Venus that don't have any satellites at all. The Earth has one big one, our moon, and Mars has two really tiny asteroid sized satellites, Phobos and Deimos. So you don't have the same kind of richness here. And with a lot of these ring systems, especially the ones around Jupiter, for instance, they're made up of very small particles. Those particles can get pushed around even by the light of the sun. And so you need to have a way to sort of replenish that material over time. And you certainly don't have that at Mercury or Venus. With the Earth, we've got a big moon and it doesn't tend to output a lot of material. So it's more difficult to make and maintain ring structures around rocky planets.
Okay. Last question about the rings, I promise. No, I'm not going to promise, but it's last planned question about the rings.
It's fun to explore them. I mean, we set 4 chapters, I think, in the Saturnian system because it's just such a fascinating and beautiful
Right.
place.
So you wrote, just one sentence from your book is, many of the true moons of Saturn live within the gaps in the rings. Now, I'll accept that as true, but that leads me to a question that you didn't answer in the book, which is, even given everything that you've said, why are there gaps in the rings? Why isn't it essentially a solid band? For all of the reasons that you said, there could be a solid band in a narrow vertical dimension, but there are gaps in the ring, so that's why there are rings and not one really thick ring. So why are there gaps in Saturn's rings? How did that happen, and why are they maintained? Why isn't there drift in and out to essentially disperse?
Oh, it's a wonderful question. And I love the terminology that we give to the moons that orbit within these gaps. We call them shepherd moons. And we call them shepherds because they kind of keep the ring particles in line. So, something that happens when you're building up any kind of dynamical system like this, whether it's the solar system writ large or whether it's the rings of Saturn, is that if you have an object of considerable size and gravity, it tends to clear all of the particles out of its path. So that's what gives you the gap in in the rings, and you can sort of see that effect on a smaller scale as well. We have a lot of smaller moons in the Saturnian rings that are working on this process a little bit. They look like little ravioli. They've sort of attracted together all of the little particles around their own equator, and maybe someday there'll be little gaps in the rings where these new moons that are coming together are forming. So you have this idea of shepherd moons that keep the edges nice and sharp and that keep the areas where they orbit free of material.
So if there's any asteroid or any rock that ventures into the orbit, when the moon swings around to that area, the gravitational pull of the moon will just pull that rock into itself, and therefore it's clear. So it might have something there for less than whatever the lunar orbit period is, but then it just gets sucked into the gravitational well of the moon, and therefore it's kept clear. Is that basically how that works?
That's right. And there are effects, gravitational effects, as the moon passes by the other ring particles that sort of keeps them in line a little bit. There's a new ring that's being formed right now from the material that jets out of Enceladus. It's called the E ring. And it's in the book. I don't have the name of the moon off at the tip of my tongue, but there's one that sort of is shaping the E ring into another nice normal ring of Saturn's. And that ring isn't sharp yet. So it has areas where it extends a little further out from the planet, a little further in. And there's this process where that moon is sort of like running into those ring particles and reshaping the ring. And it just makes me think of, like if the other ones are the ring shepherds, this is like the wolf in the system. It's sort of nipping at the heels of the sheep to keep them in line.
Okay. Another aspect of the book where I learned something right new, you talked about dwarf planets, and you said that there are 5 in our solar system, and 2 of them I'd never even heard of. So what are the 5 dwarf planets of our solar system, and can you guess which 2 I had never even heard of before?
So there's actually quite a few dwarf planets out there, and because these objects, many of them are very far away, we don't actually we have dwarf planet candidates, we call them. They haven't been confirmed yet. So ones that are thought to be very likely or that we know fit the definition of dwarf planet would be Ceres, Pluto, and then we have Quaroar. And by the way, I will certainly mispronounce some of these. We also have Sedna, Haumea, Eris, Maki Maki, Orcus, and Gong Gong. But there are a large number of bodies out there that are suspected of being dwarf planets, and we don't yet know.
Okay, so you just listed, I think, 8 dwarf planets in your book, which was published last year in 2024. You listed 5. So have we discovered 3 planets since you finished writing your book? 3 dwarf planets, excuse me, since you published your book.
Well, these are being discovered, I think, all of the time, and the ones I listed have discovery dates that are a little further in the past. So this could be one of the areas of the book where we're kind of dating ourselves a little bit to the information that was put in. But it's definitely a category that is growing over time.
Well, I mean, I guess that's what makes it exciting, right? This isn't a static piece of knowledge where you learn it once and then it's good for all time. There's still more that we're learning and that we're discovering, and that uh, as we get better telescopes, we look at more aspects of the sky. We see not just distant aspects of our own galaxy or other galaxies. We're learning a lot about our very own solar system, that our cosmic neighborhood.
Definitely, and if you want to include all the dwarf planets, the mnemonics are definitely out the window at this point.
Right. I want to sort of bring it back to the book a little bit, because that was, how I came to speak with you, and I did enjoy it. And another aspect of the structure of the book is that for each area of the solar system that you visit, on the fictional side of thing, the protagonist, which is interesting because you use the second person. You do this, you see that, you feel this when you do that sort of thing. You prepare these. The protagonist is always doing a different activity. So you're golfing on, or you're surfing, or you're hot air ballooning, or you're skydiving, or spelunking, and every place you visit, you do some different type of activity. So how did you decide what activities there were going to be, where you would locate them? I'm very curious about that, because it did lead to a bit of fun and adventure for each, to lead into each chapter.
Definitely, we gave some thought to this, thinking about, we've got a particular environment. We want to be able to explore that environment, but we can't have the protagonist, we felt, just take a walk everywhere. We wanted to have them explore something unique about that particular environment that made it really interesting, something you could do there but nowhere else, or something that compared to an activity that you might do on Earth, say in a national park, and to essentially try that out in a really alien environment to see how it might be the same and how it might be different. So that was really the device that we used to do that exploration. And I really do think that the comparison with the national parks is really key. Like, a lot of science fiction out there is about the first time anybody is somewhere. So something right at the edge of discovery. And if you're operating right at the edge of discovery, that means you've gotten there just when the technology is only barely able to do it, and we're only barely able to make that trek. And
High
so this
risk, no precedent. Yeah.
and so as an explorer, the thing that you're going to be obsessed with, and this comes through in a lot of science fiction as well, is staying alive.
Hmm.
And you don't, in fact, you aren't able to take in the scene in the same way. And so we wanted something that was a bit more accessible. We wanted to imagine, somebody essentially visiting the equivalent of a national park for the first time, because just because it's new to you, doesn't make it any less amazing than if it's new to humanity.
Right. And that comes through. Like if you're visiting a park, there's a checklist. You need a tent, you need a sleeping bag, you need food, you need pots, all the things that you're going to need. And there are checklists. You can talk to experts or just go through the list and look out for snakes and don't feed the bears and so on. And that's actually the sense that you get from reading your book. Okay, you've got your kit. You need to make sure that you've got your oxygen, you've got your pressure suit, because if that thing pops, then you'll be crushed or sucked out, depending on whether the atmospheric pressure is greater or lesser by a dramatic degree than Earth. But it's not. So of course there are dangers because it's space and on another planet, but it's also, you get a sense of routine. Okay, so you put on the suit, you make sure you double check your oxygen levels, and then you go out and you do the thing. And like the contrast between in some of the chapters, almost the pedestrian standard typical thing that hundreds of people have done. It's okay, yeah, you could have in one of your chapters, you could have gone on a guided tour, but you prefer to see this thing on your own. Like, just the implications of that are kind of mind-blowing when what you're talking about is walking on the surface of another planet. Like, we've only done that on the moon as a species, and not for decades. And that we can visit basically anywhere in the solar system the way you might take a transcontinental flight. I love this idea, and it's clearly fictional. So thank you. uh, for someone that who would you think is the ideal audience? Who would get the most from reading your book? I mean, clearly a geek like me is going to enjoy it because I did. But who did you have in mind when you were writing this book?
Well, what we wanted to do is we wanted to, talk about the actual solar system in a way that would make sense for people who were familiar with speculative fiction and science fiction, and wanted to know what it might feel like to actually be out there. And we created the book because originally we couldn't find something like that, quite like that in the world. We had some descriptions of, the exploration that had taken place with spacecraft out in the world that were very factual and very scientific. And Jesse and I mean, we love those, but we understand we're not, as professional scientists, we're not really representative of, the typical reader. So we wanted to take something from science fiction, which is very exciting, but often, even when science fiction is operating in our own solar system, the authors will cheat just a little bit to make the story more exciting, or to do something in a different way. And so what we were thinking is, actually the solar system is pretty darn incredible as it is. Why don't we try presenting it in an absolutely true way, using the device of science fiction? And then we could go ahead and talk a little bit about the actual science that informs that. And it's interesting that you mentioned earlier in the conversation, you were talking about how the idea that there's this mundane sort of component to it, that it's a place. Many of the places that we're going are not on the edge of discovery, at least not at the time that the protagonist is doing those things. And I remember after we submitted our final manuscript and we talked to the publisher, that one thing that really struck them was that they felt that the book was very optimistic. Just the fact that, you have utterly normal people able to go and visit and walk on the other planets, and to really open up their own eyes, even if many people have seen it before. The idea that we could get to that point, that It's not just doom and gloom for the future and for civilization. So the framing on its own was something that they thought was pretty unique to our own book, that optimism.
Yeah, and there is a sense of implicit optimism. I mean, if anytime we read the headlines, we're recording this towards the end of January 2025. It'll be released in the early February when people listen to it. But just the headlines of the past week or the past month, when you're looking at climate change or the fires that are raging around the world, and there's a, a high level of generalized anxiety about whether our civilization is going to make it throughout the next decade or two, never mind towards our grandchildren. And the idea of, here we are surfing Saturn's rings or hot air ballooning in Venus is it is optimistic because it means that we will continue. I mean, if your vision comes to pass in any form, it means that we will continue to gain knowledge. We will continue to increase our capabilities, our technologies, not just our scientific knowledge, and that the benefits of this increased scientific understanding of the universe and the engineering that is made possible as a result of them are widely enough distributed that normal people, that's not the right word, but that a non-exceptional individual, someone who graduated from university, is skillful enough and wealthy enough to visit other planets. It's not limited to a couple dozen out of the billions of people, and that, to my mind, is an inherently, if never explicitly stated, optimistic view of our potential and of our future.
I think you have to hope about these things. And one thing I always think of when I'm especially when I'm reading older science fiction or older speculative fiction is what that says about the people who were writing it at the time. I mean, many people I know focus on oh, does it hold up? Oh, they were so wrong about what we would have in 2025.
Well, a lot of science fiction is written as a warning, not as a prediction.
Right? Well, exactly. It's and the warning and the prediction, I think, have to do with the hopes and the aspirations of the people writing it.
Mm-hmm.
So I think there are many possible futures, for us as a species, as a civilization. And one of the exciting things that I think sometimes we forget is, collectively, we get to write that. We get to decide what we want to do.
And that's so important. You're absolutely right on that.
And so, I like that, Jesse and I are able to, add sort of like a hopeful note in there to say that, hey, here's, we're not saying that this is the future, but, maybe this is a possible future. And if you, the reader, think that, this would be exciting to be a part of, why don't we work towards something like that? So that's, I think we're coming on. I don't think we had internalized that, quite explicitly, but as the book was coming together and as we were finishing, we were realizing that there was this tone throughout this framing that implied that kind of optimistic perspective.
All right, I ask one last question for you. In a couple of places in the book, in the first half of each chapter, you hint about the possibility of life within our solar system. And I'll leave it to people to read the book itself to find out exactly how you incorporate that. But I want to ask your opinion. Do you think there is life in our solar system, not outside of planet Earth? And if not, do you think there is life in our universe, in the galaxy, beyond our tiny third rock from the sun?
Yeah, this is a good question, and even though it's a question I look at professionally, I certainly don't have the the answer to
No,
it.
I'm asking.
But
It's an open scientific question. Let's take that as a given. We do not know for certain. I am asking, as someone who studies this in part as part of your scientific career, what is your opinion?
well, within our own solar system, there are a few times and places where the conditions for life existed, and we don't know if those places. I mean, they were what we would call habitable, but we don't know whether they were inhabited then or whether they're inhabited now. I think, we can gain a little bit of strength thinking about the Earth, because the Earth became inhabited almost as soon as it was possible for it to be habitable. So you look at places like ancient Venus, for instance, or the deep subsurface of Mars, or maybe even around some of these ocean worlds like Europa and Enceladus that we've talked about earlier today. These are places where potentially life could live and thrive and survive, and especially with the ocean worlds, there's more livable volume, more habitable volume in those worlds under the surface than there is on the entire Earth. So it could be that those places are empty, but I certainly hope that they aren't. And I would love to be able to address and answer that question, hopefully in my lifetime, to learn whether or not, something actually occurred, whether there was a second genesis for life within the solar system, or potentially because planets can share material back and forth. You get rocks can be blasted off of one planet and travel to another through a process we call panspermia. Whether even more tantalizing, whether life existed in different parts of the solar system at one point that was related to one another.
Right. So if we visit another planet, we might leave behind some microbes and that are able to reproduce, or something like that. Or a meteor impacts one planet, and then something survives as it eventually lands somewhere else.
Yeah, and it has to arrive in an area where it's actually clement. So the to give you an example, the surface of Mars isn't habitable right now. It's one of the closest environments to the Earth, but it's still an awful, awful place to make a living for many, many reasons. However, when people ask the question, "Is there life on Mars?" A colleague of mine who I work with quite a bit, Professor Andy Sugar down at the University of Florida, he likes to say, "Of course, there's life on Mars." Because we sent it there. We haven't sterilized the insides of our spacecraft, and bacteria are so pervasive within the terrestrial environment that there are likely spores of bacteria that live inside the computers in the internal spaces. They can't replicate, they can't metabolize. So, for all intents and purposes, they're not actually alive, but they're things that could, do all those functions if they found an environment that was clement for them. And one thing that we do as a profession is we take a close look whenever we're sending a mission to see if it's going to arrive in a place where terrestrial life could take hold. We do that largely because we want to know what's going on there. We don't want to create a false positive. We don't want to unnecessarily contaminate another area with terrestrial organisms. But this is an interesting question that comes up as we travel the solar system and as we do our own transfer of material. Things that used to be part of the Earth now live on every other planet. So you'd also asked about the galaxy. The best answer I can give you there, I have to tip my hat to the late great Carl Sagan. Through his book Cosmos, that when it comes to life elsewhere in the galaxy and in the universe, if there is no one out there, it'd be a terrible waste of space.
Well, I think that's a wonderful sentiment to end on. John Moores, thank you so much for taking the time to speak with me today. Any last thoughts you'd like to share with our listeners? And if people are interested in finding out more from you, do you have an online presence that you'd like to share with folks?
I do. So I can be reached by email or on social media. So I'm on, I believe it's called X now, and Blue Sky. So by all means, if you'd like to connect and talk more, don't hesitate to drop me a line.
All right. Well, I'll put links to those in the show notes. John Moores, author of Daydreaming in the Solar System, Surfing Saturn's Rings, Golfing on the Moon, and Other Adventures in Space Exploration. Thank you again for talking with me today on Podcast for Inquiry. If you enjoyed today's podcast, please consider giving us a 5-star review and showing your support at patreon.com/podcastforinquiry. Email us podcast@centerforinquiry.ca. We'd love to hear your perspective. The Podcast for Inquiry is brought to you by the Centre for Inquiry Canada. We are a national educational charity supporting reason, compassion, and secular values. Help us support rational discourse and evidence-based decision-making by becoming a member at centerforinquiry.ca/join. CFIC is on the web, on Facebook, and you can follow us on Blue Sky at CFI Canada. Podcast for Inquiry is produced and edited by Zach Dumont and Martin Zielinski. Music by Anthony Lazaro. I'm your host, Leslie Rosenblatt. See you next time.